इस क्वेश्चन में हमसे पूछा गया है जब हमारे 4 हाइड्रोजन न्यूक्लियाई कंबाइन करते हैं और ये फॉर्म करते हैं एक हीलियम न्यूक्लियाई और 2 इलेक्ट्रॉन देते हैं, प्लस हमें ये 26 मेगा इलेक्ट्रॉन वोल्ट्स देते हैं ऑफ एनर्जी, तो ये जो हमारा इक्वेशन होता है ये हमें क्या रिप्रेजेंट करता है? तो हमें ऑप्शन नंबर 1 में दिया गया है बीटा डीके। अब बीटा डीके में क्या होता है? सपोज करते हैं हमारा जो x है, यहाँ पे एक एलिमेंट वो हमारा कन्वर्ट हो जाता है टू वाई, जिसका हमारा एटॉमिक नंबर जो होता है वो +1 हो जाता है, क्योंकि जो हमारे न्यूक्लियस के अंदर एक न्यूट्रॉन होता है वो हमारे प्रोटॉन में चेंज हो जाता है। इस वजह से जो हमारा एटॉमिक नंबर है वो एक इंक्रीज कर जाता है और हमारे मास नंबर पे कोई फ़र्क नहीं पड़ता। प्लस हमारा एक बीटा पार्टिकल यानी कि एक इलेक्ट्रॉन हमारा इजेक्ट हो जाता है फ्रॉम न्यूक्लियस। फिर ऑप्शन नंबर 2 में हमें दिया गया है गामा डीके, जिसके अंदर हमारा जो एक्स है एलिमेंट वो एक हायर न्यूक्लियर एनर्जी स्टेट से ग्राउंड स्टेट ऑफ न्यूक्लियस आने की कोशिश करता है। अब इस कन्वर्जन में जो हमारा रे निकलता है वो हमारा गामा रे की फ्रीक्वेंसी में बिलोंग करता है, इसलिए इसे हम गामा डीके कहते हैं। और फिर हमारा फ्यूजन होता है जिसमें हमारे बहुत सारे स्मॉल लाइट एटम्स कंबाइन करके हमें देते हैं एक बिगर एटम, और हमारे फिजन में इसका एग्जैक्टली उल्टा होता है, जिसके अंदर हमारा एक बिग एटम टूट के हमें स्मॉल एटम्स देता है। तो जो हमारा यहाँ पे रिएक्शन है उसके अंदर हम देख सकते हैं कि हमारा 4 स्मॉल लाइट हाइड्रोजन एटम कंबाइन करके हमारा हीलियम एटम में कन्वर्ट हो रहे हैं। तो इसी वजह से जो हमारा ऑप्शन नंबर 3 होगा ऑफ फ्यूजन, ये हमारा करेक्ट आंसर होगा।
Hello everyone, let us start with our question. In this question, what is given? Scientists are working hard to develop a nuclear fusion reactor. So basically, scientists are working hard to get a new nuclear fusion reactor, and they found that deuteron could be, which is also known as heavy hydrogen, could be one of the possible nuclear reactor for this case. Now, if there are two deuterons, so if they react, so there would be ionized helium which would be formed, and there would be nitrogen which would be released, and there would be some amount of energy that would be released. Now the temperature for this nuclear reactor would be very high. Okay, these are very high, and there could not be any and no material can be used to confine the plasma at for a time t0 before the particles fly away from the core. Okay, now due to high temperature. Now if n denotes the density of the deuteron, the product n into t naught is given as the Lorentz number. So this is given, and in one of the criteria, reactor is successful when Lorentz number is greater than 5 into 10 raised to the power 14 seconds per centimeter square. Okay, this is the value which has been given, and there are some constant values which have been also given. Now assume that two deuteron nuclei in the core of the fusion reactor at a temperature T are moving towards each other. Okay, with kinetic energy is given as to be 1.5 kT. When the separation between them is large enough to neglect Coulomb's energy. Also neglect any interaction is large enough to also neglect any interaction from other particle in the core. Now the minimum value of the temperature, this is what we need to find. The minimum value of the temperature required to reach a separation of 4 into 10 raised to the power minus 15 meter would be what? So how much we should there would be a temperature, okay, so that they could have a separation of 4 into 10 raised to the power minus 15 meter. Okay, this we need to find. How can we find this? So these are the values of the range of the temperature which have been given, and from A, B, C, D we need to check which of the option would be correct. Okay, how can we solve this? So first of all, because there are two deuterium atoms, okay, here it is given as two deuterium nuclei, okay, deuteron nuclei. So we can say that our that loss in the kinetic energy, we can say that loss in kinetic energy, okay, energy would be equals to gain in the electrostatic potential energy, gain in EP, electrostatic potential energy. Okay, now what is the loss in the kinetic energy? So there are two deuteron nuclei, so we say that it would be 2 times, and what is the value of each of them? It is 1.5 k into T. Okay, k into T, where k is what? K is the Boltzmann constant, T is the temperature in Kelvin. How do we write electrostatic potential energy? So it would be 1 by 4 pi epsilon 1 by 4 pi epsilon charge square. So it would be E square divided by the separation R. Now K value we know. K value is given as to be 8.6 into 10 raised to the power minus 5. We can put the value of K. So 2 into 8.6, 2 into 1.5, sorry, into 8.6 into 10 raised to the power minus 5 in terms of electron volt, and K we have put into T, temperature. Now this value E square divided by 4 pi epsilon. So this is epsilon 1.44 into 10 raised to the power minus 9. This value has also been given. So we put this value also 1.44 into 10 raised to the power minus 9. Now what is the separation? Separation is 4 into 10 raised to the power 4 into 10 raised to the power minus 15. Now this is the value of the separation. So we get this one. So we can calculate the value of T. So what would be the value of T which would be coming if we solve this? So T value would turn out to be 1.4 into 10 raised to the power 9 Kelvin. Okay. So in which limit it would be appearing? So 1.4 into 10 raised to the power minus 1.4 into 10 raised to the power 9. So 1.4 into 10 raised to the power, so it would be A, it can form in A. So it cannot form in B because it is 2. Here 10 to the power 9 is common, but it is 2 and it is 3. So here it cannot be. Here it is 3 and 4. So in all these options, it cannot be the range, because our range is what? T is equals to 1.4 into 10 raised to the power 9 Kelvin. Okay. So our correct option would be our A option. So hope you have understood this solution. Thank you.
Hello everyone. Results of calculations for 4 different designs of a fusion reactor using DD reaction are given below. Which of these is most promising based on Lawson criterion? So the question is asking us to find out that which of these given values for deuteron density and confinement time is most promising based on Lawson criterion. We know that for Lawson criterion to be promising, n multiplied by T naught should be greater than 5 into 10 raised to the power 14 SCM minus 3. As you can see, for option B, it is given to us in the question that n is equals to 8 into 10 raised to the power 14 centimeter minus cube, and confinement time, which is given by T naught, is given to us 9 into 10 raised to the power minus 1 seconds. Therefore, if we multiply these two, we can clearly see that 7.2 into 10 raised to the power 14 seconds centimeter minus cube, and this is clearly greater than 5 into 10 raised to the power 14 seconds per centimeter cube. Therefore, on this explanation, we can say that the answer is option B. Thank you.
Hello everyone, let us start with our question. In this question, what is given? That assume that the nuclear binding energy per nucleon versus the mass number is shown in the figure. Now use this plot to choose the correct choice given below. Now two statements are related with the fusion and two statements are related with the fusion. Now what is fusion? Fusion means that there would be two lighter nuclei, they would be forming a heavier nuclei, and fission is the opposite of this. That means there would be a heavier nuclei, it would be breaking into two or more component. Okay. Now in the first part, it is given that fusion of the two nuclei with mass number lying in the range 1 to 50 will release energy. That means in this range 1 to 50 would be somewhere between this range. Okay. So whether it would release energy or not. So in the A part, we need to check each and every option. Now energy would be released when binding energy would be increased. That means if binding energy final is greater than binding energy initial, then energy would be released. Energy will be released. Okay. So we need to just make this a statement. Remember, now in the first case, when the mass number is lying between 1 to 50, so we take a 2. It is the case of the fusion. So let's say one is having a mass number, let's say x, so it would be lying between 1 to 50. Another, let's say it is a smaller lighter nuclei, it is also, it would be having a mass number that would be lying between 1 to 50. Okay. So what would be the initial binding energy? So binding energy initial, so it would be BE, binding energy. Okay. Now what would be the initial binding energy? So if we see for this, per nucleon is given as to be, for the first part it is given as to be 2. So we can say that it would be 2x plus 2y, or we can say that 2 times x plus y. Now what would be the final binding energy? Now when they would be combining, what would be the final mass number? So it would be x plus y. So we can say that x plus y. So where x plus y would be lying. So if we add this, so we can say that x plus y would lie between, if we add this, so it would be 1 plus 1, it would be 2, and this would be 50 plus 50, that means 100. That means still it would be lying in this region also, because it is here it is 100. That means per energy, binding energy per nucleon, it would be equals to 2. So we can say that x plus y multiplied by 2. Okay, this would be the case. Now this and this, these are equal, that means no loss or gain of energy. So we can say that this statement, first statement, is wrong. Now in the B part, now it is lying between 51 to 100. Now for the second part, we say that x is lying between 51 to 100, and then y would also lie between 51 to 100. So if we add this, so the heavier nuclei, which would be having x plus y, it would be lying between what and what? 100 and 2. If we add this one, and then it would be 200. Now we calculate the binding energy in the initial case. Binding energy for the initial part. So for x, it is lying between 51 to 100. So this is the range. Okay. So this is the range. So we can say that it would be binding energy per nucleon is given as to be 2 for both. So it would be 2x plus 2y, or we can take 2 to be common, it would be x plus y. Why? Because it is lying in the range from till up till 100. So what would be the binding energy final? So it is lying between 102 to 200. So what is this? So that means in this range, in this it would be lying. So that means binding energy per nucleon, this factor would be 8. So this is 2, 4, 6, and then this is 8. So we can say that x plus y, this would be the number of nucleon multiplied by 8. Now clearly we can see that binding energy final is greater than binding energy initial. So we can say that heat would be released. So that means our this statement is true. Now in the third case, it is given that fission of the nuclear with the mass number range between 100 to 200. That means in this range. So there is a this fission process. That means they would be converted into two lighter nuclei. So it would release energy when the broken into two equal fragments. So whether this is right or this is wrong, this is wrong. Why? Now we can see that it is given as to be, the range is given as to be 100 to 200. 100 to 200, that means binding energy per nucleon would be equals to 8, somewhere like this. Now when it would be getting into the smaller nuclei, so what would be the mass number if we divide this by 2? So it would be lying between, somewhere between each and this lighter nuclei, it would be lying between 50 to 100. Now in case 50 to 100, what is the binding energy per nucleon? It is 2. Now we can say that if initially we are having a higher binding energy and finally we are having a lower binding energy, that means this reaction is not possible. Okay, because binding energy, when it would increase, then this would be possible. But in this case, we can see that clearly initially binding energy was 8, now it is 2. So clearly it cannot be possible. So this is not possible. Fusion of the two nuclei lying between this 100 to 200 to 260 will release energy when broken into two equal fragments. That means the individual component, this is the total, this heavier nuclei 200 to 260. So if it is breaking into two equal parts, so it would be lying between, somewhere between 100 to this lighter nuclei, it would be lying between, let's say x would be lying between 100 to 130. Now in this part, what is the binding energy per nucleon? It would be equals to, so if we see this, so it would be somewhere around 4. Now for the lighter nuclei, what is the binding energy? It is lying between 100 to 130. So 100 and 130, it would be this range. That means now the binding energy would be per nucleon, it would be 8. That means this could be possible. That means here the binding energy is greater in the final stage as compared to the binding energy in the initial stage, which is possible. So the options would be B option and the D option. Hope you understood this solution. Thank you.